The multi-agent collective construction, MACC for short, addresses the challenge of having multiple agents work together to build a designated block structure. The construction area is a discrete grid, with each cell being either a block, an agent, or air. No blocks can be placed at the border cells. Each agent can perform the following actions, demonstrated by our proposed MACC-SLIM system: enter the grid, move to the neighbor cell, deliver a block, pick up a block, leave the grid and wait. An agent can move to an adjacent cell only if the height difference is no more than one block. This formalization is based on the terms robots, a Harvard research project. However, using these robots poses a challenge, because terms is a research platform with no manufacturing or maintenance support. We propose the MACC-SLIM system to mitigate this problem. The system consists of two readily available commercial products, a simple line-following robot and a flat-laid screen. The robot has a color sensor at its bottom, allowing it to accept color-coded commands from the screen. These commands are: turn right by 90 degrees, transmitted as a blue circle, turn left by 90 degrees, assigned a purple circle, and move forward by one block, facilitated by a red circle with a line to the neighbor grid position, allowing the agent to correct its position and rotation. We have implemented these commands to match the movement instructions of the terms robots. The block manipulation instructions are performed on the screen in order to keep the system simple. The MACC-SLIM system allows the execution of plans from the state-of-the-art algorithms. The plan is selected at the start, containing a list of actions for each of the agents. The execution starts with all agents outside a grid without blocks. The agents enter, placing their blocks before going outside the grid for more. The application provides a window with a 3D visualization of the world state in the MACC discretization, shown in the top left corner. Please note the pauses the agents take. The plan is the result of a MACC model, which does not consider the turn action of the agents, requiring weight padding of the faster actions. Similar padding is placed because of enter and leave actions, where the agents outside the grid move in a queue, but the model assumes their movement around the grid to only last one time step. This simplification would, in a naive implementation, lead to waiting for the agent to go around the grid. By adding agents to a queue for a specific border cell and moving all the agents in the queue at the same time, we achieve constant time complexity of both enter and leave action. An example of the leave action queue is shown at both sides of the front agent row. Once the mission is completed, the grid is highlighted in black, followed by the visualization of the structure shifting from the top-down view of the height map to the side view used in the literature. This concludes our demonstration.